So hello everyone, this is lecture 6 for the quantum mechanics. So today we will study about the photoelectric effect. In the last lecture we have completed the Planck's theory, but I gave you some homework, so hope you tried. Let me give you the solution. First, we need to get this average energy expression h nu by kT divided by minus 1. So how we get this expression? So this came from the statistical mechanics. Now we will use the quantum mechanics to get this expression. So for the quantum harmonic oscillators, we have energy expression this n plus 1 by 2 h cut omega. So we always have this energy in the form of this. We already proved this from the Planck's theory, where n can be 0, 1, 2, 3, 4. Now to find the average energy in the statistical mechanics, we use partition function. So for the partition function, we will use this n equal to 0 to infinity. This is a summation exponential minus beta en. Whatever you want to the average value, so you will put that function here. So this is partition function. Now we'll solve this for energy. So En is nothing but n plus 1 by 2 h cut omega. So for n equal to 0 it will be h cut omega by 2, and for 1 it will be 3 by 2 h cut omega, and just substitute the values in place of En. You will get this expression. Take exponential minus beta h cut omega by 2 common. You will get this series, and this is nothing but Gp. So geometric progression, you can use the formula A Rn minus 1 divided by R minus 1. That is summation of geometric progression. So for R is means the value of R is less than 1, so you will get 1 upon 1 minus R. So this is your common ratio, this divided by this, so it will be R here. So you will get this formula. Now this is your partition function for energy. So how to find the average energy? So average energy formula will be del by del beta, and this is the log of partition function. So this is your formula. Now we will just substitute the value of Q here. So partition function value here. Now we will solve this. It will be log x minus log y. So log x upon y can be replaced by that. Now log exponential this will give you this value only, minus log of this. Now we need to find the derivative with respect to beta. So it will be h cut omega by 2 minus h cut omega by 2. It will give you minus minus plus. And for this second term, it will be log x will be 1 upon x. Then this will be 0, and derivation of this means you can find the differentiation of this term. So you will get this term, this value. Now this minus minus will be plus. This will go to the denominator. So it will give you exponential plus beta h cut omega, and this will cancel out. It will be minus 1 here. Okay. Now see, this is the ground level energy. So we will eliminate this. And now if you put h over 2 pi here and 2 pi over t here, so it will be 2 pi will cancel out. You will get h multiply 1 upon t. 1 upon t is nothing but frequency. So this will be h nu, and here also it is h nu, and beta is nothing but kt. So you will get this expression h nu divided by exponential power h nu by kt minus 1. So this will be your average energy. So that's how you get this expression for average energy, and then we use this and find the Planck's expression. Now I give you these 3 questions also to prove. Now we need to prove the Rayleigh-Jeans formula for by this formula. Okay, for the small means the condition is h nu is less than kt. Now see, this is your formula from the Planck. Now h nu is less than kt, then this whole term will be h nu by kt will be less than 1, and when exponential power x minus 1 and where x is less than 1, then we get this expression. Means exponential series of x in the Taylor expansion is 1 plus x by 1 factorial x square by 2 factorial. When x is less than 1, then these higher terms will be negligible. So we'll write exponential x as 1 plus x only. So this exponential x minus 1 will be 1 plus x minus 1, and 1 will cancel out, you will get x here. So this whole term will be nothing but h nu by kt only, and h nu will cancel out, you will get kt. So this whole term will reduce to kt only, and we know this is the formula for Rayleigh-Jeans, means when this average energy is nothing but only kt. So that's how we get the Rayleigh-Jeans law from the Planck's law. Now we need to prove the Stephen's law from the Planck's theory. So here is the proof. So you have the small energy, you will integrate for the complete energy, and that should be proportional to t to the power 4. So let's see. This is your expression for the Planck's. Now what you will do, you will just integrate as you put the integration here. So take out the constant terms out. Now inside you will have frequency cube divided by exponential h nu by kt minus 1. Now put h nu by kt equal to x. From here you can write mu equal to ktx by h. Now we need mu cube, so mu cube will be x cube, whole means all terms will be cubed. From here you can find d nu in terms of dx, so d nu will be kt over s dx. So substitute this value here and hold all these values here and take the constant terms out. So inside you will get exponential x minus 1 and here it will be x cube. So you will get this thing. These are all constants, and now this integral can be solved, and the value of this integral is pi by 15 4. And here you can see t multiplied t cube, it will give you t4. So this will be constant, and whole other things are constant, so it will be t4. So energy is proportional to t4. So that's how you proved the Stevens law. Now third one is we need to prove the Wien's displacement law. So how we get this thing? So from here, let's see. So here is the proof. This is your expression from the Planck's theory. Now this is nothing but energy, and we need to maximize this energy because Wien's displacement law works for the small wavelengths, and small wavelengths came when there is high temperature. Okay, so you get the graph something like this, and Wien's displacement law is valid for the small wavelength only. So let's see, this is your energy from the Planck's theory. Now we need to maximize this energy. For that, this whole denominator term should be maximum. So means we need to maximize the energy. So for that, this denominator term should be minimum. So let's say this is f function, okay, of the function of lambda. Now this should be minimum. So how can we make this minimum? We know if we need to minimize any function, we need to find the derivative and put it equal to 0. So we'll find the derivative of f with respect to lambda and put it equate it with 0. So derivation of this or the derivative of this will be use the product rule here. So first it will be 5 lambda 4, then it will as it is, then find the derivative of this and put the lambda 5 as it is. So you will get these terms. Now this should be equal to 0 to minimize or maximize this. Now put sc by lambda kt equal to x to simplify this equation. So we will have 5 lambda 4 exponential x minus 1 from here, and lambda 5, this is again x, so exponential x multiply sc by lambda kt will be x, so it will be x upon lambda minus x by lambda equal to 0. Now see, this is minus term, so it will go to the right hand side, and this will give you lambda 4 here, lambda will cancel out, make is lambda 4, and lambda 4 both sides will be cancelled out. So you will get 5 exponential x minus 1 equal to x exponential x. Now this exponential x will go to this side and will give you 1 minus exponential minus x, and 5 will go this side, x upon 5. Now see this expression. Means what is the value of x? X is nothing but sc by lambda kt. So Wien's displacement law is valid for the small lambda, very small lambda. So this will be very large value. So exponential minus very large value will give you very small value, because it is like if x is tending to infinity, this will tending to 0. So for large value of x, this will tending to 0, so you will get whole term as 1 only. So x will be 5. We can find value of x equal to 5 here. Now put x equal to 5 here, and you will get lambda t equal to sc by 5k. And this k is nothing but Boltzmann constant, and h is Planck's constant, c is speed of light. So see, this is your Wien's displacement law. Now you find the value of sc by 5 kb. You will get this value 2.8 into 10 to the minus 3, and this lambda is nothing but lambda max, and this is temperature, absolute temperature. So that's how you can prove the Wien's displacement law from the Planck's theory. Okay, now we can move forward now. So today's topic is photoelectric effect. So in the 1887, before the Planck's theory, there was Hertz, means this was a scientist. He did an experiment, means this was the apparatus. He placed some metal plate here, and this was cavity, and this is another metal plate. Here is battery emitter, and he put some light over it, over the metal, and he observed that, means then he observed some observations. So what were the observations? That there was current when there was this light. He gets some current. When there was no light, then there was no current. So what was the observations? Means now they don't know, still they don't know about the quantum mechanics. There is no Planck's theory, there is no quantum mechanics. Just he did the experiment, he don't know what is happening. Okay, so he see that there is some current because of something going from here to here. So he called that cathode rays. He don't know it is electron, because electron is still not discovered. Okay, so he called them cathode rays, and he made some observations. So what were the observations? We will see. Before that, I will let me tell you that in 1899, J.J. Thomson discovered the electron, and after that they come to know that this cathode rays are nothing but electrons. So before that, in the 1887, we called them cathode rays. So he called them cathode rays. So what were the observations he made at that time? So he made that observations like current I flow only when the frequency of the incident light is more than our threshold frequency. Means this frequency of light should be greater than a particular value. Only then we will observe the current. Otherwise there will be no current if it is less than that particular value. So that was the threshold frequency. He called it. And it is irrespective, means independent of the intensity of the radiation. Whatever intensity it is, it should be greater than frequency. Means it is all depending on the frequency, the current in the circuit. So this was the first observation. Second, ejection of electrons or the cathode rays is instantaneous, that is there is no detectable time difference between incident of the radiation and the ejection of the electrons. So it was completely instantaneous. When the light falls, the cathode ray is starting to emit, and time difference was approximated 10 to the minus 9 seconds. This was second observation. Third observation was for mu is greater than particular frequency, the number of electrons ejected increase with intensity but doesn't depend on the frequency. So for a particular, means now this frequency is greater than that threshold value, and now the number of electrons emitting or the cathode rays emitting is varying with intensity. Means more the intensity, more electron will emit, but it is independent of this frequency. This was the third observation. Fourth was the maximum kinetic energy of the ejected electrons or the cathode rays depends on the mu but independent of I. Means whatever intensity you are falling over it, it is the kinetic energy of the cathode rays or the electrons is independent of that intensity, but it was depending on the frequency only. So maximum kinetic energy is proportional to frequency. So these were the observations made in the 1887, and he observed these two graphs from these observations, that kinetic energy of the electrons are moving only after a particular mu naught value. Then we get this kind of curve for the kinetic energy, and also this kind means if it is current and it is voltage, then you will have some current even at the zero voltage. Then at a particular, means this is negative potential, this current will tends to zero, and if there are different intensities, they will all go to the same negative potential, that is called the stopping potential. And this is, if this is the curve, then I3 will be greater than I2 and greater than I1. Okay, so this is higher intensity, more electrons but same energy, and the energy will be same. That's how we are getting the same stopping potential. We will discuss all them. These are just the observations we are talking about now, so we'll discuss them in detail when we come to the comprehension. So what is this V naught, the stopping potential? This is at constant frequency, at particular frequency or particular intensity, the minimum negative potential at which the photocurrents becomes zero is called the stopping potential. So the amount of potential required here in the circuit, means now it is negative here and positive here, so the amount of minimum negative potential required to make the current zero, this current zero, so that is called the stopping potential. So that is meaning the velocity will be zero and kinetic energy will be zero. So that is the stopping potential. Now how to measure the kinetic energy? So see, if this is your metal sheet, then there were some electrons at the surface, and this is your conduction band only. Okay, so these are the free electrons. So, and some electrons will be inside in the depth and some will be at the surface. So for the same frequency, these electrons will have the different kinetic energy, because they are traveling from inside and they will be having some collisions and the disturbance, and extra energy will be expended, means expand here, then the electrons on the surface. So this electron will have the higher kinetic energy, this will less, this will more or less, and this will more or less. So that's how you can define the kinetic energy for different electrons for the same frequency. Now see, for the maximum kinetic energy, how you can measure the maximum kinetic energy. So let's say we have these over 4 electrons, then if this require only 0.5 electron volt energy, means at 0.5 volt this will emit, and at 1 volt this will emit, at 1.5 volt this will emit, and 2 volt this will emit. So these are the, means this is the potential or the voltage we are applying from here. Means if this is the electron totally inside, this electron for the 0.5 electron volt is at the surface. So very minimum or the 0.5 volt potential is only required to stop the electron completely. Okay, so means the maximum kinetic energy is depending on the potential. or the voltage applied from here. So Kmax is nothing but E V naught. Whatever you are applying from here, this is equal to this. Okay. So that is the Kmax. That's how you can find the Kmax. So always remember this. Now these were the observations, and these were the observations actually made in the 1887 by the Hertz and the other scientists. So now when the means what was the failure, means they know at that time what is the classical theory and what were the contradictions according to the classical theory at that time. So first failure was when mu is greater than mu naught, I is not equal to 0, means at only after particular frequency the current is in the circuit. Means for the, if we talk about the classical theory, then in that the energy depending on the amplitude of electric field square. Okay, means the energy, or means for any frequency, according to the classical theory, for any frequency you can emit the electron, because if it is emitting less energy or giving the less energy, then after a very long time it will get the enough or sufficient energy to emit the electron. But the intensity of I proportional to amplitude of E square, any frequency with sufficient I intensity can supply the necessary energy to liberate electron from the metal surface. But it was not happening there. Means for the particular means before the particular frequency, less than that frequency, there were no electrons, whether there is very high intensity there, but this electron was not emitting. So you can take this as like we have a magnifying glass and you are trying to burn a paper from the sunlight, then you concentrate the whole intensity at a single point, then that's how you can increase the intensity and can emit the electron. But if you are even increasing the intensity, this electron is not emitting here in the photoelectric effect. Okay, so it is emitting only after a particular frequency. So this was the very much failure, okay, and the contradiction which was not satisfying here. So this was a very big thing. Now try to solve this question, you will get a better idea what I was talking here. So it was let's see the question. A metal plate is placed 1 meter from light source. Assume that an electron may collect its energy from a circular area of plate of radius 1 angstrom. The energy required to remove an electron from the metal surface is 2.1 electron volt. Prove that the time taken by photoelectrons to eject out of metal surface will be. So we need to solve this question according to the classical theory. We don't know the quantum theory yet. So what is the question saying? That you need to find that if this is your source and it is emitting 1 watt power, means 1 joule per second energy it is emitting, then electron at this metal, this is 1 meter distance, and at this metal this electron will absorb only energy which is around 1 angstrom radius. So whatever energy you are getting from here, the electron getting from here, the electron will use only that energy to emit. So how much time it will take to emit this electron? Means use the classical theory, means first find the energy at this point. How you can find? This is 1 joule per second at here. Now this is emitting from here, means this area is 4 pi r square for the sphere. So energy per unit area will be 1 watt divided by 4 pi r square. Now you need to find the energy at this point. So find this circular area will be pi r square where radius is 1 angstrom. So at this point multiply this area, then you will find the energy at this point. Okay, so energy per unit area find from here, then at this area find the energy, then use that energy, means now this amount of energy is falling and total energy required is 2.1 volt. So divide that this energy by that energy, so you will get the time. So try to prove this, that for 1 watt energy you will get 2.3 minutes, and for 0.1 watt you will get 23.3 minutes, for 10 to the minus 3 watt you will get 38 hours. So try to solve it, otherwise I will give you the solution in the next lecture. Now this was also the failure, means the second it was, means electrons are emitting instantaneously here. Okay, in the experimental observations electrons are emitting instantaneously. But if we see that from the classical theory in this question, we are seeing that for the less amount of energy we are getting long time to emit electron, and for higher energy we are getting less time. So it is depending on the how much energy we are providing. But in the real or the experimental observation we are seeing that it is emitting instantaneously. It is not depending on the how much energy we are applying or the intensity we are applying. It should be just greater than that particular frequency. So this was also the contradiction from the classical theory. And third was that kinetic energy of the electrons are depending on the frequency. means higher the frequency, higher the kinetic energy. But according to the classical theory, intensity depending on the energy or the electric field, means higher the energy you will apply from the, means intensity, higher the intensity you will apply, more the force will be applied on the electrons. So according to the classical theory, more intensity, more energy it will get, then more force will be applied, and more will be the force, or the force, then more will be its motion and the kinetic energy. So according to the classical theory, this should follow, but it follows this thing, not this thing. It is not depending, kinetic energy is not depending on the energy or the intensity. I mean, it is depending on energy, but it is not depending on the intensity or the electric field. Okay. So what happened, it was in the 1900, then when Max Planck gives his Planck theory. Then after that, in 1905, Einstein re-explained this whole photoelectric effect in his own theory. Okay, so Einstein never did the experiment, he just explained the photoelectric effect using the Planck's theory, and for this he get the Nobel Prize. So there was two equations, means first Max Planck gives this NH nu, then there was this modified version of Planck's law given by the Einstein. So in real, Einstein never did the experiment, practical experiments. He just explained the these observations, whatever contradictions we were having. So he explained all these things very well using the Planck's theory in the 1905. So in the next lecture, we will study about the photoelectric effect according to the Einstein, means Einstein theory, or the Einstein's modified version. Okay, so version of photoelectric effect given by the Einstein. So we will study about that, and we will discuss this question first, then we will move forward. So okay, for today, let's end today's lecture here. Thank you everyone.